All right, as I mentioned in the previous video for problem 1 on the exam 2 review, I have some Matlab stuff that I'd like you to take a look at. This is using a live script from Matlab. I just read about those and I wish I'd been using these all through the course. But the nice thing about a live script in Matlab is you can put some graphics and you can add some text and explain what's going on with the problem. All right, so in this case, we had looked at the closed loop transfer function, the error signal transfer function, and calculated steady state error for both a step reference input and a ramp reference input. So let's take a look at how this would go in Matlab. Okay, we had an undetermined parameter k, so let's go ahead and specify k to be 4. And the first thing we do is we define the system components, so we have to make this a transfer function object. I'd hope you could do that on the exam. And then we identify there's D, here's G, and here's H, and we just type those in, okay? One of the things we did on this problem, we looked at the steady state error. You can calculate the steady state error transfer function. This is what you get. And the thing I wanted to notice about that is that mentally you could do this calculation for steady state error. We know this is a type 1 system, so we know that the error goes to 0. But if we let R of S be a unit step, and even if you scale it by 3, R of S would be 3 over S. And then that would cancel with the S from the final value theorem. And so essentially we'd be looking at 3 times E and take the limit as S goes to 0. Well, you notice here in the transfer function, there's an S. There's S's in all the terms. When you let S equal 0, the steady state error term goes to 0 in the long run. Okay, so I wanted to point that out. All right, so the next thing that I'd like you to be able to do and prove that you can do on an exam is to write MATLAB commands that show the step response. Okay, so in this particular case, it's just a simple thing. All I'm expecting would be step of 3 times the transfer function t. Remember, we defined t up here. So 3 times t, and then this just tells you how long to plot it. I don't care about that. So the answer on an exam would be just step 3 times t. All right, so I went ahead and plotted that and added some things to make the plot look nice. And so here is the response, and you see it heads towards 3. And so remember the reference signal was 3. So you can see the steady state error is in fact 0 for this case. All right, for the next part, I thought this was interesting. You can't find a ramp response in MATLAB like you do step. There's no equivalent ramp function. However, if you consider how this is developed, you take the transfer function and you multiply by S. And I'm sorry, you take the transfer function and you multiply by R. For a unit step, R is 1 over S. And so that's already factored into this function. For a unit ramp, the Laplace transform is 1 over S squared. So if you wanted the ramp response for something that has a slope of 4, you could take 4 times the transfer function, so 4 is the slope, and then divide that by S. Because you already have a division by S from the step response, this would in fact give you the ramp response. Okay, so I wanted you to know about that, and so I can calculate that, and you can see the response of this system. It starts out and it tries to track the ramp, and it has a little bit of steady state error. Okay, now what might be confusing to you is this steady state error looks less than what we calculated it to be. Okay, so we calculated, for k equal 4, the steady state error would be 1. And if you check here, we can look in MATLAB, the difference between the error at this point and at this point, the difference of between these two lines is 0.4187, not 1. Okay, and so what's going on? Well, what's going on is we have feedback, y, going through this transfer function s over s plus 7. Okay, at one point in the course we talked about how this form of a transfer function is a low-pass filter. So we're actually filtering the output before we get it into the summer. It's supposed to be negative feedback here, by the way. All All right, so because it's filtered, we are actually looking at something different than just output minus the reference, okay? So when you look at those loops, the error signal, when there's more than unity feedback, when there's an H in the feedback loop, the error signal is R minus Y times H, okay? And so, what I wanted to show next is you could calculate the response for the filtered version of Y, all right? So the filtered version of Y is you take Y and you pass it through the filter H and you get the output. I'm calling that output Y subscript H, okay? So we can plot that and you see it's tracking along, and if you look carefully, there's about a 1 unit difference between the blue line and the red line, or the top line and the bottom line. And you can actually calculate that carefully using Matlab, and you see, yes, indeed, in this interpretation where you have to worry about the filtered output, the steady state error is 1, okay? And the last thing I added here is you can find the error response for a ramp input. We're just looking at the error signal. So remember, the error signal transfer function would be 4 because we're looking at a slope of 4, divided by s because the other s is incorporated into the step function. And you'd actually could look at the error signal, which is the difference between the ramp and the filtered output y. And this heads towards 4 over k, where k is equal to 4. It heads towards 1 like we expected. Okay, so those are some MATLAB things that go along with problem number 1.